Microsoft chair for the program, and has been here despite lots of commitments of family and directorship of department and so on. She's been here for 4 weeks during the program, which was a great pleasure. Isabelle is very well known in the geophysical PDE community, and she's an exceptional professor of mathematics as of this year, I discovered, which is a funny French quirk, but it's really a big pleasure to introduce you, and she'll talk to us about betaplane models. Right. Thank you very much. Do you know all the...
Yeah, I think, is this working? Seems to be,
yes,
right?
Okay.
Yeah, thank you.
Thank you.
Okay, well, first, of course, I'd like to thank the organizers of this program for inviting me. It's been really a pleasure to be here to talk to different people from different communities. It's very nice. I'm sure this workshop will also be very successful. So, okay, so I'd like to talk about the shallow water equations. So I think the title of my talk was something like Trapping of Rossby Waves. Okay, in the, okay, around the equator, right? Let's say in the equatorial model. So the plan of my talk will be first, of course, to explain briefly the model, which is a quite simple model, but which still allows you to see a few geophysical, well, interesting phenomena. So I'll try to explain that. Then, so what I'd like to do on the model, which is a shallow water rotating model. Then what I'll try to do is explain how from this nonlinear system of PDEs you can extract some waves, in particular Rossby waves, and understand their propagation. Okay, so I'll tell you a little bit where this question came from. So this comes from a series of works I've done with Laure Saint-Raymond, who's also in Paris. So we were studying different models which were supposed to describe some geophysical fluids. At some point we were interested in the betaplane model, which is a model for rotating fluids near the equator. And we were reading the book by Podlowski, which I'm sure you all know. And at some point in his book he says something like that Rossby waves are trapped in the vicinity of the equator. But by trapped, I don't think he meant trapped in the x2 direction, in the latitude coordinates, but he actually meant in the longitude coordinates. There are some so-called ventilation zones where Rossby waves are supposed to be trapped. So we were trying to understand mathematically how you can prove such a result. Okay, so to do that, actually this is a joint work, two papers with Laure Saint-Raymond. One is also with Christophe Chevery from Rennes and Thierry Paul. And the other one is with Laure and Thierry Henry. So you can find the papers on my webpage if you're interested. Okay, so let me explain a little bit about the models. We're looking at the shallow water equations, which describe the evolution of a fluid, obviously in shallow water. Okay, and the velocity of the fluid I'll call for the moment V, which has two components, V1 and V2, and the height of the water I'll call H. Okay, just for a few minutes actually. Okay, so the general equations are the following. You have the mass conservation. Okay, and then the momentum, which starts like this. And then you remember that you have the rotation of the Earth. So if the moment I'll call omega, so there all this has the dimensions for the moment, right? Density is 1. I didn't put the density because I've just taken it equal to 1. Okay, but it should be everywhere here. And then omega will be the velocity, well, the rotation of the Earth. V perpendicular is minus V2, V1. Okay, so that's rotation. And then you have kind of stratification. And on the right-hand side, I'll put any force, bulk forces, I'll call tau. Okay? So that's the general model. But now I'm going to make some assumptions. So the main assumption is that the movement I'm looking at is very localized in some sense, meaning that I have some stationary flow, okay? and then I'm going to look at a perturbation around that stationary flow. Okay, so the perturbation will be localized in space, in a small region of space, whereas a stationary flow is a global, large-scale flow. So I'll call h bar the mean height, which will be basically 1 kilometer. Okay, and I'll call v bar a stationary solution. Okay, so h bar is 1. And okay, so here I have tau, and v bar should be divergence free because of the first equation here. Okay, so you build a stationary flow satisfying this equation in some sense. Okay, and then I want to look at a perturbation around this v bar, h bar. Okay, so I'm going to start putting dimensions also, so I have an equation with no dimensions. So I'll call T0 the typical time scale. So if you read Podolsky's book, he's going to say that those Rossby waves are trapped for a few weeks. Okay, so a typical time scale will be something like a week. The observation scale, or a few weeks. Okay, a typical horizontal scale would be something like 10 to the 4 kilometers. Okay, and then you start putting all this into the equation, and you're going to ask omega to be also rescaled by function b over capital omega, which is the speed of rotation of the Earth. Okay, so capital omega should be 7.3 10 to the minus 5 second minus 1. And b will be a function only of the latitude. Okay, so I'll call x1 the longitude in Cartesian coordinates, x2 the latitude. And I'm going to assume both of them are in R. Okay, this is not very physical, but what's going to happen is that what you expect is that in x2 everything will be confined near the equator. Okay, so there won't be any boundary problems. And in x1 we're going to try to prove there is confinement as well. So I won't put any boundaries. I'm very far from any boundaries, right? And I just assume x1 is in R. So that's not physical, but it helps a lot. Okay, so then I want to put everything with no dimensions, and I want to perturb those stationary solutions. So I'll call U the perturbation. So it's v minus v bar over some average mean velocity, which will be my scaling. Maybe v0 will be something like, so it's very small. But small perturbations around this stationary flow. That's U, which I'll also call v over v0 minus u bar. So u bar is the non-dimensionalized stationary flow. Okay, so that's my the velocity I'll be looking for. And then the height I'll be looking for is, again, a perturbation. And delta h here would be something like 1 kilometer. Is that it? No, less than that, sorry. Meter, I guess. Okay, so once you've put all those parameters in your equation, I'll call epsilon something like 10 to the minus 1, which will be actually the fruit number. And the Rossby number will be the square of the fruit number. And in the end, the equation you come up with, so I won't show you how you get those, but that's the system I'll be interested in for the whole talk, is the following. So I have the mass conservation, which becomes this, plus a nonlinear term, which is actually very small. Okay, it's very small because I'm looking at very small perturbations of the stationary flow. And then I have an equation on U, which is the following. So I have the rotation, stratification, rotation, and the fact that I'm linearizing over U bar in some sense, and then a nonlinear term. Okay. So this is the general equation. So of course I'm going to try to write it in a more compact way because it's hard to follow exactly where each term comes from. So you see you have a linear part here. Okay, well actually here too. Okay. And then a nonlinear part, okay, which is very small again. So for most of the talk, we'll just forget about the nonlinear part altogether. But before forgetting it, maybe I just want to change variables one last time, and then we won't touch the variables anymore, just to make this nonlinear term symmetric. Okay, so there's a very usual way using what we call the sound speed transformation, which allows to put this nonlinear term into a symmetric form. Okay, so to do that, that's my last change of variables. My final unknown is capital U, which was U0, which I'm going to define now. U1 and U2 are the two components of the velocity U. And U0 is just a change of variables, which you have to come up with, which is something like this. Because of all the epsilons, it doesn't look very good, but if you can just try it, then you'll see it works. Okay, so you believe me that if you do this change of variables, okay, if there are no epsilons, it looks like the sound speed transformation when you have compressible Euler equations. So in the end, if you believe this change of variables, this is the final system I want to look at. What I'll also do is multiply the whole equation by epsilon squared, so I don't have 1 over epsilons in the equation. So in the end, the equation you come up with is epsilon squared dtu plus some operator A, which depends on x because B depends on x because U bar depends on x. Okay, so it's variable coefficients. Then you see if you multiply this equation by epsilon squared, maybe I should do this now. What happens here is that, so this goes away, you have an epsilon in front of the derivative and an epsilon in front. I like to write it like this. Is that it? No, that's it. Here I multiply by epsilon squared. Here this just goes away. And so what happens is that you see that you have everywhere a factor epsilon in front of the derivatives, and then sometimes some extra factors of epsilon. Okay, and this is important because that means that the linear term here is not an operator depending on x and derivatives. It's an operator depending on x and epsilon derivatives. Okay, so everywhere here I have epsilon derivatives, and maybe some other epsilons hanging around, and a non-linear term which is symmetric, which I won't write. So I have two symmetric matrices, S1 and S2. Okay, again, S1 acts on epsilon D1, S2 epsilon D2. And I'll write down the matrix A. Somewhere, maybe I'll write it down here. Well, okay, I'll write it down over there. I can try to keep it. Okay, so matrix A, I just have straight normal derivatives with no epsilons. So if you just look at the system which is here, you can see terms on the diagonal. Okay, this is a diagonal term, it acts on eta. This too is transport acting on u. Okay, so I write it as a function of derivatives. Can you see what's written here, basically? Okay, so I have something on the diagonal, just a transport operator. And then I have off-diagonal terms, which are d1, d2, which come from the stratification. And I have the rotation here, which is minus b and b. Okay, plus some terms of order epsilon. Epsilon squared times density. So those terms of order epsilon squared, I'd like to forget for this talk. They're very, very small. Okay, and you can believe me, we can forget them. Okay, so this is the matrix, the linear propagator. Okay, and then I have a nonlinear term here and here. Okay, so what are the questions I'm interested in? Okay, so question one obviously is what about well-posedness of the system? So to study well-posedness, I need to understand it's better. I need to understand what the functional setting should be. So this we have to define. And question two, my problem is understanding waves and their propagation. So can I extract from this linear operator, can I extract waves on which my solutions will be, on which they'll be living, and how are those propagated? Okay, so that's what I'll try to explain today. So, okay, so to answer the well-posedness question, I need to understand what function space my initial data and my solutions should be living in. Okay, so if you look at this system here, you see it, as I said, everything that comes out, I don't have just derivatives, I have epsilon derivatives. So if my functions don't depend on epsilon in the sense that they're living at a scale 1, if I take a derivative and I multiply it by epsilon, it just goes to 0. So that's no interest. Okay? What I need is for my functions to live at a scale which makes epsilon derivatives order 1. Okay? If not everything goes to 0, I have a stationary solution, it's no interest. Okay, so I need a functional setting. So before giving precise definitions, what I need is functions to have scales of order epsilon, okay? Which means physically that my perturbations are localized in space. Okay, I'm somewhere in the middle of the ocean at a scale epsilon. Okay, and if I want an epsilon derivative to be order 1, an example, okay, which will be, of course, we'll look at more general things, but an example would be a function which has a frequency psi, but I'm oscillating at frequency psi over epsilon. Okay, so if you take an epsilon derivative of this thing, this looks like psi, it's order 1. Okay, so I need things to oscillate like psi over epsilon. Okay, that's just an example, of course. I'll try to do something better. So the point is, I need function spaces for which, when I take an epsilon derivative, I have something of order 1. So I'll call those spaces, in some sense, epsilon Sobolev spaces, right? Meaning that the norm of a function in this space will be just you take epsilon derivatives to the power alpha for any alpha smaller than m, apply to u, and you take the L2 norm squared. Okay, and I want my initial data, and if possible the solution, to have order 1 norms in this setting. Of course, if they don't depend on epsilon, that norm just goes to 0, except for the L2 norm. Okay, but if they look like this example here, then it's okay. It's order 1. Okay, so those are Sobolev spaces. There's one drawback, which could be a problem for well-posedness. You can check that very easily just using the usual proof of Sobolev embeddings, that if you take a function u, you compute its L infinity norm in 2 dimensions, and you assume that your u is in some HS space. Well, you know, if you don't have any epsilons, if it's normal HS spaces, this is just a constant whenever s is larger than 2. Sorry, it's greater than 2. Okay, s larger than 1. Okay, it's just a Sobolev embedding. Now, if you're in HS epsilon spaces, unfortunately, you lose an epsilon. Okay, that's just if you write the usual proof of Sobolev embeddings, just look at what happens, and epsilons come out. Okay, that's true. Of course, if you look at this example here, this is stupid because the L infinity norm of this function is fixed. Okay, so it's clearly not optimal for this kind of initial data, right? But if I just take initial data, which is in this HS epsilon space, then that's what I can prove, nothing better. Yeah.
It's obvious that the norm that we define, whatever you call the HM epsilon depends on epsilon, but it looks to me like the space is still HM.
Yeah, it is HM. Just the norm depends on epsilon.
Yeah.
Okay.
All right.
Right.
Yeah.
It's
Obviously, not
it's
depend on
HM.
epsilon. Yeah.
Of course, yes, I agree. The space is HM, but the way I measure the norm, the size is depends on epsilon. Okay, so so this just tells you I might have a problem to prove even well-posedness on a uniform time interval because I'm losing powers of epsilon when I do estimates. Okay, now if I look at the system here, of course I forgot epsilon 3 here, which was here. Okay, and now I'm okay because you see I have epsilon squared. I lose an epsilon in my energy estimate with my L infinity bound, but I have epsilon 3 here, so it's okay. Okay, so because my perturbation is very, very small, everything has been set so that things work, of course, my nonlinear term here will not be a problem. Okay, so we can really forget about it for existence on time 1. Okay, so now the question I'm wondering about is, can I find waves associated to this system? Question 1. Well, question 2 actually, and question 1 may be again, if I take initial data like this, can I propagate through the equation? Well, probably, because I have epsilon derivatives everywhere. But more generally, what does it look like? What does this initial data, which is in this space, look like really? Is it only the example up there, or are there more general examples? Okay, so the general framework for this is what people call semi-classical analysis, which is very useful first to study this kind of operators, study how it propagates, to study how different types of operators interact one with the other. That's one thing. And also, it's very useful to understand the propagation of waves. Okay, so maybe just in a few minutes, I'd like to give you a crash course in this subject. Okay, so it's going to be very, very rough, but it just will explain to you how to deal with this kind of an operator in general. Okay, so all I'm saying here, of course, it applies to this system, but it's supposed to be a much more general and robust method. People use it a lot, actually, also in control theory, because when you have this kind of a setting, you understand where waves go. When you know where waves go, you can control them. in control theory, this is really very useful as well. So let me just explain a little bit what I mean by semi-classical analysis. This is just one particular case of microlocal analysis, where instead of dealing with operators, you want to work in an easier framework, which is the framework of symbols. For instance, if you look at my example up there, I said if I have an epsilon derivative, which is a semi-classical operator, then when I apply it to my oscillation up there, what I come up with is IXE. Okay? So instead of working with epsilon derivatives, I could try to work at the level of a symbol, IXE, which is much easier, right? It's just an R or RD. Okay? If my operator is just a multiplication, then obviously at the level of a symbol nothing has happened. I have to take multiplication by x. X is not, it's x, the number x, right? It's not a multiplication. Now if my symbol is ix dot psi, what happens at the level of the operator? Well, if I believe what's written up here, I just say it's the operator, my symbol is ix dot psi. Then at the level of the operator, I replace xi by epsilon gradients. I have epsilon x gradient. Okay? If my symbol is xi dot x, which is the same, well, at the level of the operator, something's happening, right? Because if I just replace xi by epsilon gradient, I have this. Okay, so applied some function f, it's different, right? I have the same symbol, but two different operators. What's happening here is that at the level of symbols here, I'm just describing what I call principal symbols. Right? Because if I compare those two operators, what's the difference between them? Well, the difference is just epsilon. Epsilon identity. Okay? So actually, those two symbols, those two operators are very close, up to an epsilon. Okay? And they have the same principal symbol. So the idea of semi-classical analysis is to say, I'm looking at operators, depending on epsilon derivatives, and what really interests me is their principal symbol. Okay, that gives me all the information in some sense, well, a lot of information. Okay. Now, of course, the operator might have a symbol which is much more complicated, because if you take this full operator and you compute it, what you get exactly is epsilon x gradient plus epsilon x. Okay, so the symbol maybe should be ix psi plus epsilon. Okay, because there's this additional term here. But the principal symbol is the same. Okay. So what do principal symbols? Why do they help us? Well, first of all, maybe we should find a general way of giving yourself a symbol. How do I find an operator? Okay. So the way to quantize a symbol is the following: if I give myself a symbol a, I apply it to a function f. Okay, that gives me an operator. I have a formula, a way of replacing a symbol, a function of x and psi, into an operator depending on x and epsilon gradients. Okay, the formula is the following. So first of all, assume A is the identity, maybe it'll be easier. So what I'm going to do is just write Fourier and inverse Fourier. So if I had no epsilons anywhere, this is f of x, right? If I integrate in psi as well. Okay, so take A equal to 1. This is identity, right? Because I'm semi-classical, I should divide everything by epsilon. Okay, and then I should add the symbol here. And then you have a choice, right? Because the symbol depends on x and psi. So here, what should I put? Should I put x? Should I put y? Well, you can do whatever you want, actually. So what I'll do first, so of course I have no room. So then it's really your choice. The way to replace a symbol by an operator depends on what you want to do. Okay, so I have a parameter t, which is between 0 and 1. Okay, and let's check, depending on the value of t, if I put a symbol here, what operator do I get on the other side? Okay, so obviously if my symbol is just x, right, well, what's going to come out on the other side? 1 minus tx goes out. Then I'm integrating ty f of y. There's no variable xi, so when I integrate x and xi, I get x equal to y, so x gives x. Okay, if I have ixi, I just integrate by parts. Okay, there's no x dependence. Ixi here, integrate by parts, it gives me a gradient y. integrating psi gives me gradient x. Epsilon gradient x. Okay? Just by integrations by parts. Now, maybe more interestingly, if I have Ix psi, okay? So suppose, for instance, t is equal to 0. Okay? Then there's no dependence on y. X goes out. And then I'm just left with Ixi, and I know Ixi is epsilon gradient. So this is the operator I get. Right? If t is equal to 1, then I have no x, I just have y's. So it's yf, which is inside. Okay, so I have a derivative of xf. Okay, so depending on the way I quantize, I get different operators. But the principal symbol is always the same, whatever the way I quantize things. Principal symbol is always this one. Okay, so you can choose the way you want to quantize your symbol, but it doesn't really matter as long as principal symbols are concerned, it'll be always the same. Okay, so usually often what people choose is t equal to 1/2, which is the while quantization, which we'll be doing here, but anyway, we won't be doing much computation, so we won't really see it. What's interesting about the while quantization is that if your symbol is real, for instance, then your operator is self-adjoint. Okay, which is useful. Just look at the principal symbol, right? It doesn't matter if the tails have eyes in it, okay? Lower order symbols are complex. The principal symbol is real, then the operator, full operator, is self-adjoint. Okay. So maybe the last thing I want to say about this is how waves are propagated, which will be exactly what we're worried about today. So the semi-classical setting is really made for understanding how waves can be propagated. So the way to see that is take initial data, which is very, very localized in phase space and frequency in space variables. Okay. If you satisfy a transport equation, then you know exactly how your support in frequency and in space will move on with time. So I need to understand what the support is first, or more precisely the microlocal support. So I'll give you the definition and then we'll see an example, okay? Because the definition doesn't look very nice. So, okay, I'll say a function f is microlocally supported in some compact set k, which is in phase space, right? So in dimension 2, I'd be in R4, okay, t star R2. Okay, so I have my k somewhere, and I take any point in frequency space which is not in k. Okay, so k is here. I take a point in phase space which is far away from k. I take a compactly supported function, a smooth compactly supported function outside of k. Okay, equal to 1, for instance, near that point. Okay, so take a little function here. And then you compute the integral I wrote up here. Apply to chi, for instance, I'll take the while quantization, that doesn't matter. Apply it to my function f. Okay, so that's exactly the same function as I wrote up here, except that my symbol here is exactly the truncation, chi. Okay, this has to be very, very small, which I write O of epsilon infinity, meaning epsilon n for any n. In L2, for instance. Okay, epsilon infinity means smaller than any power of epsilon in L2. Okay, so this is a definition. So maybe I'll just give one example, and then we'll move on to applications. So the usual example you should have in mind, maybe the only one which really explains what's going on is what we call a wave packet, which is a Gaussian in space. Okay, and then you want to normalize this, so you're in L2, so I think that's normalization. So this is a Gaussian, right? And then you have this frequency of oscillation. And what I claim is that this function here, its microlocal support is just the points Q and P. Okay, should we check this? So to check this, what you do is you stick this formula into the integral here, okay? Forget about this epsilon, because anyway you want to have something very, very small, so you don't care about powers of epsilon here. This can go away. And then you just write down what the phase is. So you have an oscillating integral. The phase is x minus y psi. Forget about the 1 over epsilon, which is everywhere. And then I'll try to get this right. Minus y minus q squared over 2. Plus I, this is an I, y minus q p. Okay, that's the phase. So I have an oscillating integral. I want to know if this integral is very, very, very small. To make it very, very small, you want to use a non-stationary phase theorem. Okay, if the gradient of this phase does not vanish, then you can integrate by parts as much as you want. Every time I integrate by part, I get a power of epsilon. So in the end, I get this. Okay, so I just need the phase, the gradient of the phase not to vanish. And if you compute the gradient of the phase in the variable y, what I get is I psi minus p minus y minus q. Okay? So if my function chi is supported far from p and q, this cannot be 0, and this cannot be 0. Okay, so gradient doesn't vanish, you can integrate by parts as much as you want, and you're happy. Okay, so it works. So if you don't like this horrible formula, which I can understand, you can just think of this kind of example. Okay, so the initial data I'm looking at are, for instance, Gaussians, oscillating Gaussians, which are very much localized somewhere in frequency and in space. Okay? Now, what does semi-classical tell you about this kind of a localization? So that's the last thing I want to tell you about. And then we can try to apply it to our system. Yeah.
Can't be anything, right? I mean, you got to make it arbitrarily small.
Sorry?
Your set K.
Yeah.
I mean, there must be a minimum size by the uncertainty principle, no? Is it?
Yes, of course, but it's 1, let's say. For a moment, everything is of size 1. I've rescaled everything, right? X and size, and everything's of size 1. Right. Of course, if in general, if you're in microlocal with no scaling, then you have to be careful, of course, about how psi and x talk to each other because of the uncertainty principle. But here, just take everything equal to 1. K is in phase space, right? Okay, so the last very important result, actually, which we'll be using very much in the sequel, is how the micro support, microlocal support, propagate. So the general result I'll be using is the following. So this I can't prove right now because it's just it's long to prove. But if you have a transport equation with the following scaling, so it's important here I have an I because I'm going to look at a self-adjoint operator here. So if you don't have an I, this has to be a skew set self-adjoint. Okay, assume A is real if this is a wild quantization. Or anyway, whatever happens, you want this to be self-adjoint. So again, if you have wild quantization, just look at the principal symbol, it has to be real. Then you know you're self-adjoint. Okay, so I look at this equation. This is an equation, not a system. And I assume my initial data has a micro support in some compact sets K0. Okay, so compact set in phase space. That's my assumption. Then the theorem, which is due to Pierre Williams and Thierry Paul, tells you exactly where K is going in time. Okay, the theorem tells you that for any finite time, the micro support, so for any time t smaller than some capital T, the micro support of f of time t, which is kt, is propagated by the Hamiltonian curves associated with the principal symbol of A, meaning the following curves: x dot is equal to gradient psi A0, psi dot is equal to minus gradient x A0, where A0 is the principal symbol. Principal symbol, right, is the order 1 term. Okay, so this is very, very convenient, right? If you know exactly where your initial data is, then you know for all times, all finite times. Actually, you can do better. You can put a log epsilon if you want. Okay, but let's say for all finite times, you know exactly where your support is going. So you know exactly where your function is localized. Okay, in x and in psi. So when you have that, you can say, you can try to study Rossby waves, for instance, right? If I know what my initial data is, I can try to show there's trapping, because I know exactly that the Rossby waves will be following this kind of a curve, of course, once I know what the Rossby principal symbol is. Okay? So this is really interesting. The only thing you have to remember here is that you have a scaling, right? Right, so I'm saying here this time is finite, any finite time, meaning if you have no epsilon here, that means a very, very long time, 1 over epsilon. That epsilon squared here, it means a very short time. Okay, it just depends on the scaling of time. Okay, if you want an order 1 time here, then you have to have an epsilon dt. Okay, so maybe what I can do now is state the theorem, and we'll end the talk by proving parts of it. Okay, so let me state the result. So there were several questions. I wanted to know first if the system was well posed, meaning on a uniform time interval. And then we want to find waves, and we want to see how they propagate. Okay, so the results is the following. So first result concerns the full nonlinear equation, which is somewhere here. Okay, so I need to have smooth enough initial data. We didn't really care about how smooth it could be. We didn't try to optimize this at all. So I assume I have 4 derivatives in the longitude direction, which is probably much too much, but we didn't really worry about that. And then in the latitude direction, I'll try to explain this. We assume not only derivatives, but also some decay. So this is bounded in L2. Okay, so it's sort of the semi-classical symbolic space, except here there's this thing.
We can think of V of x2 as just x2.
Yes. If you're on the betaplane, this is x2 squared. This is the harmonic oscillator. Okay, but so actually everything I could say here, I could leave for this, but just since it's worse for any b, I prefer put any b going to infinity. Sorry, I need b to go to infinity when x2 goes to infinity. Okay, if you have this, then the system is well posed on a time, so I won't be too precise, but on a time t star epsilon, which is bounded from below by some uniform time. Okay, well posed meaning you have uniqueness of solutions in the same space. Okay, and that holds on a uniform time interval. Okay. Okay, so as I said, then we just forget about the nonlinear term because it's very small, and all I want to study now are waves. I want to look at the linear system. Okay, where A is still the matrix which is over there, and I want to study waves associated with this linear system. So the result is the following. First of all, for any finite time, you can write, well, it can be positive or negative, let's say positive. You can write the epsilon as the sum of a Poincaré vector field plus a Rossby vector field. Okay, meaning that this P here means my solution is sitting on a Poincaré wave, which we'll be describing later on. And this one is the other part sitting on a Rossby wave, which again we'll be making precise later on. So what happens to those waves? Well, first of all, let's study the Rossby wave. So in general, what you can prove is not very much. You can just prove that if you look at the microsupport in x2, okay, so I just want to look at what the support in the latitude variable of v epsilon r of t. I know it lies in a compact set for all times. Okay, which is really not a surprise, and well, as you'll see in the proof, and this was known for a long time, and that's not the answer we were looking for. We wanted a real localization in x and also in the longitude direction. Okay, this is just a latitude. So we're not able to prove the latitude confinement in general, but only if the u bar, which is the thing against which we're linearizing in some sense, is a shear flow. Okay, which is very particular, but still. And if it's not identically positive. So that we're pretty happy with this, actually with this assumption, because what you can read in books also is that Rossby waves are trapped only if you have something stopping them. Okay, Rossby waves propagate to the east, and this means that you have something propagating to the west, which is stopping them. Okay, so this assumption sometimes is reasonable. Okay, you need to have your flow, the mean flow, to be coming back in some sense. Okay, then there is some set lambda in phase space such that if my initial data has a microsupport in lambda, then the support in x, so especially in x1 of the Rossby part, is also in a compact set for all times. Okay, it's a bit loosely written, but I'm saying if my initial data is somewhere in phase space, this is codimension 1, it's not too small, you can check that, or you can prove that, then it's true that your waves are trapped. Okay, in the longitude direction also. Okay, and maybe I'll tell you right now how they're trapped if I don't have time later on. What happens is that, so the x2 direction is easy to say it's trapped. In the longitude direction, what happens is that you're going to, the x2 is going to 0 of u1, okay, where it stops, where u1 stops. It's not identically positive, so it gets, at some point it gets 0, right? And x2 is going to that point, and x1 is also asymptotically going to a limit, actually. Okay. So that's one thing. And then what about Poincaré waves, since they're there? We should describe them. So Poincaré waves have a very different scale. As we'll see, so very high frequency in some sense. And what happens is that they satisfy the dispersive estimates, saying that if you give yourself any compact set k, any positive time, you can prove that your Poincaré waves at time t in L2 of that compact set k is as small as you want. Okay, so that's a local decay of energy in some sense, okay, which is quite strong, which tells you that Poincaré waves leave any compact set as soon as t is positive. So they go away very, very fast. Okay. Of course, this physically is a bit stupid, because if that's true, then something has to happen, right? Because we're not in the whole space. So there should be, at some point, they're going to touch the boundary. I don't know what happens there. So that would be interesting to put boundary conditions on those waves, either to absorb them or see how they reflect. Okay, this I don't know. Okay. Okay, so that's the end of the theorem, and maybe I'll give you some elements of proof. So at the beginning of the talk, I cheated a little bit because I told you, remember, this has an epsilon 3 here. So there is no problem for well-posedness, because I lose an epsilon by the symbolic embedding, but I gain it because I have one more here than there. So I told you then you're fine with well-posedness. Actually, you're not fine, because you have this linear term. Okay? So if you want to prove this result, you're going to take derivatives of your equation and start writing energy estimates. Okay, but if I take a derivative of this equation, I know A here is Q-symmetric. Okay, which is very important, because if it wasn't the first energy estimate you make, you lose 1 over epsilon squared. Okay, so you really need this to be Q-symmetric, even in just to have an energy estimate in L2. Okay, but then if you start taking derivatives, you're going to have to look at the commutator between A and an epsilon derivative. Right, because I'm going to take epsilon derivatives in those spaces up there. But if you do that, well, you say, I'm very happy because I know semi-classical analysis tells me I gain an epsilon. Remember, we said the principal symbol is the same, so the commutator, you have an epsilon. Okay? But you're not happy because here you have epsilon squared. Okay, so if I take one commutator, this is of order epsilon, so I still have a 1 over epsilon in my estimate. So I don't have a uniform bound. Okay? So I need to do something more clever than just taking straight epsilon derivatives. And that's why I have that space up there with the b squared of x2, right? Because this, basically, this operator, so epsilon 1 d1 is okay, it commutes at any order, so it's 0, or epsilon squared, actually. Why? Because if I have a d1, you look at the matrix, at first order, when you start taking derivatives, the only dependence on x1 is this. There's already order epsilon, so I take one more commutator, have epsilon squared. Okay, so that's fine. But epsilon d2 is very bad. If I take a commutator with epsilon d2, then because of the b in the equation, in the matrix, I'm only of order epsilon. But what you should do is take this. Maybe take it twice, and then you have a gain. Okay, so this actually was known, not exactly in the setting, but almost in a paper by Dutrifoy, Maida, and Shahut. So they did that exactly in the betaplane situation with x2 squared. Not semi-classical, so it's much harder. You need to control all the terms. Okay, and they found an operator which basically commutes with the matrix. In our case, it's easier because since we're semi-classical, we can afford losing epsilons, and so we can take any function b, it works as well. But that's the general idea. Okay, so once you've done this, then point 1 is easy to prove, so I won't do it. And I'd rather move on to the Rossby and Poincaré waves. So point 1 is done. Now what I need to do is understand how from this equation with this matrix A, I'm able to find waves. Okay, and in some sense, what I want to do is diagonalize my system, right? I have this equation, epsilon squared dt v plus AV is equal to 0. That's a system, a 3x3 system, and I want to replace it by 3 equations, semi-classical type equations. Okay, and one equation will be Poincaré equation, the other one will be Rossby equation, roughly. So I need to diagonalize this matrix. Okay, so actually there are 2 ways to do it. Well, you can try brute force. Okay, so that we did actually with Lorsaint-Raymond a long time ago. When u bar was equal to 0, and when b was equal to x2, that's in a very particular situation. So you don't have any large-scale flow, and then you're in the betaplane situation. Then you can just try brute force. Okay, diagonalize this in the way you can. And we did manage to do that, and we found 3 eigenvalues. So this was not semi-classical, actually, there was no epsilon. But I just want to show you the eigenvalues to compare what we'll do here. So we had 2 types of Poincaré eigenvalues, which were plus or minus I. I is because they're skew symmetric. What we did was in the x1 variable, we could take Fourier because there's no dependence in x1 because u bar was 0. So psi1 is just a Fourier variable. And then we had, okay, let's put an epsilon to compare better. Beta epsilon 2n plus 1. So our eigenvalues were quantized. You had the Fourier variable here, and n was any integer. And of course, you recognize here the harmonic oscillator eigenvalues. So what happened was that in psi1 you had Fourier, and in x1 you had Fourier, and x2 you had the harmonic oscillator. Okay, that was for the Poincaré waves, and the Rossby waves were much smaller. There was an epsilon here, so it's beta x2. And then at the denominator you had the same. So 2 comments. So that's an old result we had a long time ago. First comment is that you have a different scale. Okay, Poincaré waves are order 1, Rossby waves are very small. Second comment, you have Fourier in x1, which we won't have in general because u bar depends on x1, and you have the harmonic oscillator in x2. Okay. Now this, we didn't manage to do anything brute force because everything depends on x1 and x2, no Fourier, no nothing. So what we did was use semi-classical analysis. What it tells you is that when you have an operator, every time you see epsilon gradients, just replace it by I xi. Okay, so the principal value, the matrix of principal values, the principal the matrix of principal symbols, everything which is order epsilon you just put to 0 because I want a principal symbol, and then what I get here is psi1, I xi1, I xi2, 0, 0, minus bb. Okay, so principal symbols here, that's a very easy matrix to diagonalize. Okay, and you get 3 eigenvalues, tau plus 1, which is I square root of psi1 squared plus psi2 squared plus b squared. And then the last one, maybe not yet Rossby, which is 0, unfortunately. Okay? So actually it's very reasonable to find that, right? Because here if b squared is the harmonic oscillator, if b squared is x squared, then this is the harmonic oscillator. Right, so that's the same term as that. And 0 here is obvious because we should expect the Rossby waves to be order epsilon, so they're not in the principal symbol. Okay, so that's a real problem actually, because to my knowledge there was no general theory to find from a general matrix of pseudo-differential operators how to diagonalize it in general. Okay, so we had to work a little bit, but maybe I won't explain that now. But in the end we were able to find the next order. Okay, and the next order, I'll write up here. So the Rossby wave, or maybe I should call it the epsilon Rossby, So it's, of course it's an epsilon in front of it because it's a lower order term. And you have the first part, which is b prime psi 1 over what's down there. And then you have the transport term, which appears again, u bar I u bar x. Okay, so that's exactly the same as what we had before, except this was quantized as eigenvalues. Okay, this is symbols. And then you have the transport term, which wasn't there before. I. Okay, so now we're in the correct setting to start doing analysis, right? Yes, sorry.
Why are they not quantized?
Because I'm not looking for eigenvalues. I'm looking for, I want to replace a system, a 3x3 system of pseudo-differential equations by three pseudo-differential equations. I'm not looking for an explicit diagonalization here. Okay, it's a different, sort of different point of view. They're linked in the sense that I could then I could come back from this and find an operator whose eigenvalues are this. Okay, so I could find three equations. But there I'm looking directly, I have this matrix of operators, I want to replace it by three equations with operators. Okay, so it's linked, but it's not exactly the same thing. Here I'm looking for eigenvalues, here I'm looking for operators directly. Okay. So in the end what we've done, okay, I'll state the result here. So what we've done is replaced the 3x3 system by three equations. Okay, I have one equation. I can write. I'll write the solution phi. Okay, so maybe I should put i's everywhere so I don't have. Okay, phi is equal to 0. That's a Rossby equation. Okay, I had epsilon squared in my equation before, and since my Rossby eigenvalues are of order epsilon, I can divide everything by epsilon. So I have exactly this equation, which has exactly the right setting for semi-classical analysis, right? Epsilon dt. And then I have two Poincaré equations. So those are principal symbols, actually, right? It's not the full symbol. But I can find the full symbol if I want. Poincaré, plus or minus. When should I stop, Beatrice? 5 minutes, okay. So I'm almost finished in the sense that I found my waves. Okay, now I have three equations. I can try to use semi-classical analysis to just solve the problem. Okay, so for the Rossby case, I'm exactly in the right situation. I can just study the Hamiltonian curves. Okay, so Hamiltonian curves are just studying x dot equals grading psi tau Rossby, principal symbol, and minus gradient x tau Rossby principal symbol. Principal symbol is here, it's explicit. So I just have to look at it and try to see that some things are closed. Okay, so it's not totally trivial because it's a two-dimensional dynamical system, well, four-dimensional. Okay, so for me it's pretty hard to study. So that's why very quickly we assumed this was just a function of u2 of x2, and sometimes it becomes one-dimensional. Okay, which is easier. And okay, so maybe I'll just show you why the x2 is trapped for Rossby. Actually, the reason is quite simple. You know that when you have Hamiltonian curves, they live on energy surfaces. Okay, so you know that all those curves live on tau r0 equal to a constant. So you know that b prime psi 1 over psi squared plus b squared plus u psi 1 has to be a constant. Okay, now assume that x2 goes to infinity. Okay, you want to prove x2 is trapped, so you just assume it goes to infinity. What happens? Okay, of course I forgot to tell you, but you can assume that u bar is compactly supported. Okay, because u bar is a stationary solution, you can assume that tau is compactly supported if it's forcing by wind or something. So if u bar is compactly supported, as soon as x2 goes to infinity, this goes away after some time. Okay, then when x2 goes to infinity, since b is going to infinity, this also goes to 0. Okay, so the only possibility for x2 to be not trapped, okay, to leave the equator, is to be on a zero energy surface. That's the first remark. Then assume you're on a zero energy surface and do the same reasoning. If x2 goes to infinity, this goes away. So you have to have at some point b prime of x2 is equal to 0, or psi 1 at that point. is equal to 0, right? You're looking at your curve on your energy surface, which is a 0 energy surface. Assume x2 goes to infinity. At some point, it exits the support of u bar. And since this is equal to 0, then b prime psi 1 has to be equal to 0. But it's easy to see that if b prime is equal to 0, or if psi 1 is equal to 0, then gradient psi 2 of tau is equal to 0, which means that x2 dot is equal to 0, which means you're a fixed point. Okay, so actually, whatever happens, x2 has to be trapped for any u bar, compactly supported. Okay, I think I have to stop now. So to prove x1 is trapped is just, I can't show you, it's just looking at those equations and working on them quite hard, thinking, and then it works, but it's not so easy. And okay, to prove dispersion of Poincaré waves, it relies on a bit more sophisticated techniques because of the long time scale here. Okay, so you have to use what's known as Moore estimates, which are another technology. Moore, Mr. Moore from Marseille, who basically tells you that if you can compute very easily that the commutator between the Poincaré operator and just x1, that's positive in some sense. You can just compute it because it's easy to compute the principal symbol of such a bracket. Your formulas for that, you see this is positive, and Moore tells you if you commute an operator with something and you get something positive, then that means that you're going to be pushed in the direction of that something. So x1 is going to be pushed as far as you want to infinity, and just it disperses. Okay, so that's one line saying what a Moore estimate is. But once you have that, then you're done. You know that x1 goes to infinity. And I'll stop now. Thank you very much.
Why don't you use the p prime greater than 0 condition? You need not p prime, the background flow has to be...
Change the sign?
Yeah.
It's hidden in everything I didn't tell you. It's trapped at x1.
Yeah.
At some point, you have this equation you want to look at. It's very messy, right? You look at the equation on x1, and you know that you restrict to the 0 eigen energy because that's easier in some sense. Okay, so those trapped Rossby waves are actually at 0 energy. Then you look at the equation x1 should satisfy, and you see that when u bar changes sign, right, then your x1 goes to a loop. It's
the result is that some waves are trapped.
yes, some. And it's some kind of an if and only if, actually. The lambda we have here, if I don't write it exactly like that, if I say just that the L2 norm should not be O of epsilon infinity, which is, it can be very, very small, but not...
But it's not that all the waves are trapped.
No.
It's just, physically, right, you just take the wavelength short enough that the Doppler shift is dominant.
Say that again?
Well, I'm saying that what you do to get those trapped waves is that you take the wavelength short enough so your psi 1 psi 2 large enough.
Right, psi 2 gets very, very large.
And then the Doppler shift is dominant. Then you put your waves precisely where the flow is.
Maybe that's probably exactly what we're doing. But maybe I'll try. Thanks. I have to see that again, yeah.
Yes.
Probably.
There is epsilon squared terms that have been dropped.
Yeah.
Can one go and recheck that they remain small under these time scales and special scales of interest?
Oh yeah, definitely. Yeah, I dropped them just for today, but
In the beginning, but the question is can one, because you have a solution now, which you know some of its norms. The question: do the norms of the solution that you have, these terms are still small?
Yeah.
The time scales of interest.
Yes. Yeah. Because the theorem is really you give yourself a time t star, and the time scale is epsilon squared dt, but the t star is 1. So the time scale is 1 over epsilon squared. And those terms, the nonlinear terms are so small.
Yeah, well, because you see, they are small, usually an ODE term.
Yeah.
The PDE terms, the word small is really make me nervous.
I understand, but in semi-class, I know I was very nervous too, but now I'm used to this. In this setting, it's absolutely certain the epsilon means. Small just means epsilon times something, and this thing is bounded.
Maybe a couple more.
Yes. What's your precise assumption on U bar? Because if it's really crazy, then surely they start working.
Well, it depends what crazy means. It's just smooth as you want.
Okay, so
That was the answer to
then
crazy.
it's fine, yes.
Yeah, very, very smooth.
Yeah, could you say a bit about how it relates to the kind of usual equatorial wave solutions? So there you'd have a Rossby wave to inertial gravity waves, but also a Kelvin wave. And
Yeah,
a
you don't
Rossby
see the
gravity.
Kelvin wave is actually a Poincaré wave. It's a special Poincaré wave, right? The Kelvin wave is just, if I remember correctly, Kelvin wave is just psi1, right? Right? So it's a special case of Poincaré wave.
Okay, what about the mixed Rossby?
The mixed
gravity?
Rossby ENI or mixed Rossby Poincaré, which we can also call ENI, I think.
Yeah.
It's a good question. If you have epsilon equal to 1, you definitely see them, right? But with this scaling, in some sense, they're...
Well, I mean, it looks like a Poincaré wave for small wave numbers. For large wave
Yeah,
numbers.
yeah, exactly. I think they're in the Poincaré, but you can't extract them as easily. When you have an epsilon, you really have 3 types of waves, right? You have the Rossby, the ENI, and those Poincaré ones. The Rossbys are gone away because of that, are really very, very low frequency, and all the others are in the Poincaré ones.
Okay.
And then it depends on how high those frequencies are to distinguish, from what I understand, the ENI and the Poincaré. They're all there.
Okay, I think we'll stop the questions now because we will have coffee breaks and wine breaks, and we're here all week to ask questions. Just thank Isabelle again for a wonderful